In today's video, I'm going to go through your test review for Calculus Unit 9, Part 1, and this is all about the test for convergence of series. So first question, the infinite series AN has the nth partial sum Sn equals 2n minus 3 over 3n plus 2. What is the sum of the series? Well, if we have a formula for the partial sum, then the sum is going to be the limit as n goes to infinity of that partial sum. It's one of the few that if we have this information, we can actually find a value for the sum. The limit is 2/3, so the sum would be 2/3. Okay, this next one. If the limit as n goes to infinity of our nth term, our uth term, equals 0, then the series may or may converge, may or may not converge. So it might converge or diverge. Okay, this is an inconclusive test. Okay, if the limit doesn't equal 0, however, if we're adding something infinitely that is not 0, that is a mandatory diverge. That is our divergence test. Or the nth term test. Okay, and then the converse, or the contrapositive, I guess, if the series blank, then the limit has to equal 0. If you know that you have a convergent series, then the limit must have been 0. Now, the flip of that's not true. If the limit does equal 0, it could be convergent, could be divergent. But if you know it's convergent, then the terms had to go to 0 for that to happen. The integral test confirms that this series converges. So if we use the integral test, we would have looked at this. So this question is asking, what is that improper integral? So when we have an improper integral, remember we use limits to make it become proper. Okay, this integral is pretty straightforward. You may need to remember how to do a u substitution for your test, just saying. But the antiderivative of this is just tangent inverse. So we want the limit as b goes to infinity of the tangent inverse of b minus the tangent inverse of 1. Okay, well, as we go to infinity, we like tangent inverse just pops up a lot because it is kind of unique in that its graph has a finite limit as you go to both infinity and negative infinity. So in this case, as we go to infinity, tangent inverse goes to pi over 2. Tangent inverse of 1 is pi over 4. So our value here is pi over 4. So what are all the values that this series converges? Okay, so what we're looking at here is really the degrees. The top of this has a degree 3. So we want to think about what the degree of this numerator or the denominator would have to be to make this convergent. Well, if you think about the limit comparison test, we can compare this to a p-series. Okay. If I compared this to, say, like the harmonic series, if I had the degree here exactly one higher, say this was a degree 4, then we could compare it to a harmonic, which would be divergent. But I want this to converge. So what I want is this to be greater than one higher than this numerator. Okay, in this case, that means I want 3a minus 4 to be greater than 4. If it equals 4, then it's going to be divergent because we'd compare it to harmonic. But if it was just a teensy bit higher, then it would be compared to a p-series with a degree greater than 1, which is convergent. And we just do some quick algebra to get our value. So again, in order for it to converge, we want this to be greater than 1 higher the degree of the numerator. Okay, next one, this is kind of leading us to the ratio test. We're not actually doing the ratio test. We're finding that limit without really making the conclusion. So when we do the ratio, nth plus 1 term is going to be n plus 1, 2 to the n plus 1 over n plus 1 factorial over that nth term. Obviously this is messy, but there's lots of stuff we can do to simplify. Okay. N plus 1 is just going to stay n plus 1. Not a whole lot we can do right now. 2 to the n plus 1 is the same as 2 to the n times an additional 2. N plus 1 factorial is n plus 1 times n factorial. And we'll multiply by the reciprocal. Okay, then we look at the stuff that we can cross off, which always tends to be a lot with these. 2 to the n's cancel, n plus 1's cancel, n factorials cancel. So the things that made the cut here, on top I've got this 2. On the bottom I have n. This limit as we go to infinity is 0. Okay, we're next looking at which of these series cannot be shown to diverge using the limit comparison test with the series 1 over n. So with the limit comparison, if the limit of this over this or vice versa is a finite value, then they have the same behavior. Either they both converge or diverge. So in this case, they would both diverge. So we're going to look at this. Okay, so okay, if we multiply by that reciprocal, we end up with 3n squared over 4n squared, which reduces to 3/4. So that's a finite value, so we can use that one to show. So that's not going to work. Here, same thing. I can look at the limit of the ratio. When I multiply by the reciprocal, we get a 3n on the top and the square root of n squared on the bottom. So those essentially have the same degree, loosely. So degree 1 over degree 1. So the ratio of the leading coefficients is 3 over 1, which is 3, which is finite. Okay, this next one, if I do the limit, this limit isn't quite as straightforward. But if we go to infinity, this is going to go to 0, this is going to go to 0, and sine of 0 is 0. If we have a limit and we have 0 over 0, we bring in L'Hopital. So take the derivative, not forgetting the chain rule. Those end up canceling, so we're looking at the limit as n goes to infinity of cosine 1 over n. Okay, which means that's going to 0. So we're looking at the cosine of 0, which is 1, which is another finite value. Okay, so process of elimination leads us to D, but let's go ahead and confirm. Okay, if I reduce this, we have the same denominators. So this is the same as the limit as n goes to infinity of 2 natural log of n. As we go to infinity, that's going to go to infinity. So this one, the limit comparison test will not work with 1 over n. So that's our answer. Okay, for what positive constant will both of these converge? Okay, well this is an alternating series. So it's going to converge as long as it is alternating. Okay, because this is the alternating harmonic. So in order for this to alternate, we need that k to be an odd value. Okay, this guy right here, this is an infinite geometric. If I make this 2/3 or 4/3 or whatever, we have a geometric. We want the infinite geometric series to have a ratio of less than 1. So in this case, I need k to be less than 3. Well, we're looking for an odd value that is less than 3 and positive. So an odd positive would give me a value of 1 in this case. Which of these are absolutely convergent? So remember, we're looking take away the alternator and see what's left. Okay, here this would be a P series with a P of 2/3. Okay, which means this one diverges. Okay, the alternating series is going to converge, but the non-alternating does not. So that one is out. This one is a harmonic. So it diverges. Okay, this one, if I look at that limit, so I'm automatically saying that's going to be a limit of 4/3. Okay, and if the nth term goes to anything other than 0, this one diverges. Okay, keep going. These last two are both infinite geometric. But one of them diverges. One of them converges, because this one has a common ratio of 2/3, which means this one converges absolutely, because the alternating series, or the absolute value, converges as well as the alternating series. Okay, conditionally convergent means that the absolute value of the series diverges, but the alternating series converges. Okay, so we want to look at the absolute value. So here I'm looking at 1 over n to the 4th. That's a P series with a P of 4, which means this one converges. And if the absolute value one converges, the alternating one also converges. Okay, which is absolutely convergent, not conditionally convergent. This one is also a P series. This one's P value, however, is 2/3. Okay, if P is 2/3, that series diverges. Okay, so it passes, it's not going to be absolutely convergent. We want to make sure the alternating series also converges. So first looking at the limit as n goes to infinity. Okay, that's going to go to 0. And then to determine if it's decreasing, negative 2/3 x, and I guess not x, to the negative 5/3, we subtract 1, which is always going to be negative. So this one conditionally converges because the absolute value diverges, but the alternating converges. Last one, this is our classic harmonic, alternating harmonic, which is our classic example of conditionally convergent because the alternating series does converge, the absolute value does not. Next, we have a bunch of infinite geometric series. So infinite geometric series have a sum. It's one of the few infinite series that we can actually find the sum. If and only if the common ratio is between -1 and 1. If that common ratio does happen to be between -1 and 1, then we can find the sum with the formula a1 over 1 minus r. Okay, this one, r is 1. So this diverges. Cannot find the sum because we need it to be specifically between -1 and 1. Here, my r is negative 2/3, so that's good to go. If I plug in a 1, this is negative 2/3 times 3, so my a1 is 2. So I can go ahead and find the sum. Okay, get a common denominator. So this would be 3/3 plus 2/3 is 5/3, and then multiply by the reciprocal. So this is an a1 of -2. So we get -6/5. Okay, down here, similar, we're just swapping out a positive 2/3, and my a1 is, if I plug in 1, 2, my r is 2/3. We get a common denominator, which is 2 divided by 1/3, or 6. This one, we're out of luck because our common ratio is 3/2, which is not between -1 and 1. Diverges. This one across the top, we're multiplying by 2. On the bottom, we're multiplying by 7. So we'll have 3/4 divided by 1 minus 2/7. (21 over 20). All right, in this next section, you get to decide what test to use, apply the test, and make your conclusion. You must make a conclusion, either convergent or divergent, based on the test, and your supporting work needs to be any work necessary for that particular test. So as we're deciding, okay, you're looking at your general term here and seeing what you can find out. Is it a test or is it a series that we know? Is there an obvious issue? This first one has an obvious issue. I'm going to use the nth term test or the divergence test. Because my issue is, if I look at the limit as n goes to infinity of 2n plus 3 over 3n plus 2, I get 2/3. Okay, and according to the divergence test and just common sense, okay, if that doesn't equal 0, if we're adding an infinite number of things, they must equal 0 for it to converge. So this is a divergent series. Okay, the next two are p-series. So those are easy. We just have to decide what our p is and how does that affect its convergence. So here p is 5 over 4. Here p is 4 over 5. Okay, this is greater than 1. This is less than 1. If it's greater than 1, our series converges. In a p-series, if the number is less than 1, it diverges. Okay, if it's not a series that we readily know, then we have to run into one of our other tests. But one of our nice convenient tests is if this is sort of like one of our known tests, then we can use the limit comparison test. Okay, you could potentially use the direct comparison test, but the limit comparison for a problem like this, if there's not anything weird, limit comparison, you're not going to run into some of the issues that the direct comparison test has. So I'm going to compare this to you can do 1 over n or 1 over 2n. Either of those are fine. This is harmonic, and it diverges. What we're going to find is this plus 1 isn't really going to affect it too much. So if I look at the limit as n goes to infinity, and it doesn't matter the order here, but we get the limit as n goes to infinity, 2n over 2n plus 1, which is finite, which means they behave the same. So if this one diverges, this one diverges. So with that, you're just looking for, is this pretty similar to one of our known series? Okay, this next one. Anytime you've got a integral or a series that has natural log and 1 over x, or in this case 1 over n, that's asking you to use the integral test. You might be able to successfully use a different one, but this is really leading us to our integral test. For the integral test, we want to show that it's positive, sure, decreasing as we go to infinity, yep, and continuous. So we're going to evaluate the integral from 2 to infinity of 1 over x ln x cubed. We will use a u substitution here of natural log, purpose being du is 1 over x. This also is an improper integral, so we want to use our limits. then we get something we can integrate pretty easily. Even easier if we write it as a power. So we'll use our power rule, which is to add 1 to this power, which would be u to the negative 2. And then we need to multiply by the reciprocal of that. Before I use my limits of integration, I'm going to go ahead and substitute back in the natural log. So we're going to have negative 1/2, and I'm going to go ahead and put it in the denominator. And then we will evaluate and see what happens. Okay, so we get through that. The piece that we really care about is as b goes to infinity. So as b goes to infinity, this denominator is going to go to infinity, which means that whole term goes to 0. So it has a value, which is really all I care about. Okay, if we get a value, that means this converges. Our next one here, anytime you get those exponentials and those factorials, that's saying we want the ratio test. So ratio test, we're looking at the limit as n goes to infinity of the nth plus 1 term over the nth term. And as always, those factorials, those exponentials can be broken down. 3 to the n plus 1 is the same as 3 to the n times 3. N plus 1 factorial is n plus 1 times n factorial. Multiply by the reciprocal. Cross off a bunch of stuff. Okay, and we get 0 for the ratio test we're comparing to 1. It is less than 1, so this series converges. Okay, this next one is sort of like a series, I know, but we can't really, limit comparison might be a little bit tricky with that sign. So we're actually going to use the direct comparison in this case. Okay, I'm going to compare it, well, I'm going to build the series. I know that sine of x or sine of n is less than or equal to 1. Okay, absolute value of it is greater than or equal to 1. If I divide it by 2 to the n, it's still going to be less than that. So this series is less than or equal to this series. Well, what's special about this series? This series is an infinite geometric series. Common ratio is 1/2, which means this one converges. If the big series converges, the little series converges. Okay, our last one. The giveaway here is we have an alternating piece, which means we're going to use the alternating series test. Which has two things. First, take away the alternator, and does the limit as n go to infinity of our nth term go to 0? Why, yes it does. Then we want to look at, is it strictly decreasing? And one nice tool we have is the derivative. This will be a quotient. over the denominator squared. So we get n squared plus 1 minus, take this derivative as 2n times n. Okay, this is going to be 2n squared, so I get a negative 2n, well, negative n squared plus 1, which is going to decrease. It's going to be negative for all values bigger than 1. So this one passes the alternating series test, so this converges. Next, we're going to determine if the series converges conditionally, absolutely, or diverges. Now, this first one we already know, but we'll go ahead and run through the test. Does this converge absolutely? If I take away that alternating piece, we get 1 over n, which is harmonic, which is divergent. Okay, so this is not absolutely convergent, but it may be and will be conditionally. Okay, so we're going to look at our alternating series test. Okay, the limit equals 0. Good. If I take the derivative, we get negative 1 over n squared, which is always going to be negative. So this converges conditionally. Because the absolute value one does not converge, but the alternating one does. This next one, if I look at this, okay, take away this or not, the limit as n goes to infinity, so we get 3 halves here, which doesn't equal 0. And that's going to be the case whether we have an alternating piece or not. This series is just not going to converge. Okay, the last one. Okay, this is our funny looking alternator, but that's what it is. Turns from negative 1 to 1. So absolutely, if I look at the series 1 over n squared, that's a good old-fashioned p-series test, where my p is 2, which is greater than 1, which means this converges. Okay, if the absolute value converges, then they both converge, so we say this converges absolutely. All right, so we're going to kind of value for 1 over n that diverges, but 1 over 2p, or n to the 2p, converges. Okay, so there's different values I'm sure you can come up with. I just look at this and go, well, if I let p equal 1, that one's harmonic, which diverges. This one's a p-series, which converges. That one, p-series, and this p-series converges. You might be able to come up with another one, but one seems pretty darn easy to me. So this is what you need to know for your Unit 9 Part 1 test.